Hey, John here. Taking a trip down memory lane. Thanks a lot, Bob. One of my patrons gave me a copy of this book. This is copyright 1980, the Master IC cookbook here. And what's in here is basically the all the chips that were available to the hobbyists back in those days. I mean, I remember designing my first Z80 board circa 1979, 1980, 81. In that window of time, why don't we take a closer look at what was available back in those days and kind of contrast it to what's available to be used today for the same general purpose?
As always, thanks to all my Patreons and subscribers. You make all this possible, especially the VIPs. Thank you very much. All right, let's take a closer look at what's inside here before we get too much into this. So this is, like I said, the copyright date on this thing is 1980, right? First printing 1980, second printing, blah, 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 1980. Tab books, very popular back in the day. To find tab books in your local Radio Shack and other stores like that, where you might buy, integrated circuits and resistors and transistors and stuff to make your home projects out of. So this was the master cookbook. What do we have back then? You had your CMOS, exotic CMOS, linear, and TTL. Okay. I spent 99% of my time with TTL. Linear parts include things like voltage regulators and stuff like that. So this was what I used back in the day. I generally did not use CMOS chips because they were not as well. I mean, I didn't need to, and they had these are more sensitive to static electricity and things like that. They have different characteristics than TTL does, and we'll talk more about the difference between these two in a few minutes, because this is, as we get into the modern era, these getting a little bit mixed together now. But back in the day, things were pretty simple. If you were to build yourself a nice, motherboard with a 6502 or a Z80 on it or a 6800 or whatever you wanted to go with, you'd use, buy your CPU and a bunch of TTL chips and a couple of linear regulators. That's what you did. All right. I was there. That's how I remember it anyway. So let's look at the TTL chips, because these are what you would buy for a lot of the logic for the sort of thing that I did anyway. All right, here we go. TTL starts on page 204, right? There you go. And they get the list of, here's all the chips that they have in here, starting with the 7400 and then the 1, the 2, 3, 4, 5, and up through all these various numbers. And there'll be like the 138. We're familiar with this if you follow along my Z80 retro board and so on. And of course, the 7400 NAND gates, and what do we got? The 244 buffer driver chip and stuff like that. 23050. Oh, it's not even in here. Well, you don't have a 74 244. That would have been an LS 244. I'm still surprised it was not yet available in 1980. They were certainly, well, you got a book that's copyright 1980. It was probably written in 1978. But yes, they were definitely available in 1981. So I guess this was not the master very long. Well, the reason we're looking at this, by the way, is I wanted you to see these headings in here, because what this book does talk about is your 7400 family, your series, and this is about logic families, right? Well, even the 7400 kind of has, maybe it has subfamilies, right? But these are different families in their own right, and that is the 7400, okay? The 74L00, the 74LS00, the 74H00, the 74S00, and so on. Now look at these numbers right here. This is time for propagation delay. Okay, typical, it says. Different gates may be a little bit differently, or different manufacturer. 3.1 nanoseconds or something. All right, versus 3 or whatever. So on average, the typical 74 S00 chip would take 3 nanoseconds for the a stable signal on pins 1 and 2 to flow through here, propagate, we say, through the gate, and have a valid signal coming out on pin 3. And you could count on that pin 3 or pin 6 or whatever, the output of these four, any one of the 4 gates, will be valid and correct within 3 nanoseconds of the time that the signals are stable on the inputs. That's what that means. If you buy a 74H chip, it'll take longer. It'll take 6 nanoseconds. An LS will take 9.5. 7400 will take 10. 74L will take 33. Okay? So why don't you just buy S? Why do that? Well, they want a couple of reasons. Look at the power consumption here. If it goes fast, it uses more power. 19 milliwatts per gate if you buy a 74S versus a 7400, which will only take 10. Or an LS, which only takes 2. Holy mackerel, that's a good deal, right? So, so when you go from 7400 to 74LS, the time here is almost the same, and yet you're dividing by 5 in terms of power, okay? Now, there's other differences too, like LS does not necessarily have the same drive capacity. If you get into more specs, there's a lot more details about everything else. In addition to these general parameters up here, what we call the fan out of the outputs of each of these gates, which is the number of other chips and stuff that you can connect up to here. How many, if I come out with this signal, can I put 50 more NAND gates or OR gates or whatever connected up to here? No. Usually it's like 7 or something like that. It turns out the 7400s can drive more output than the 74LS does. Okay, so a lot of these things, you got to weigh them together, right? As a general rule, though, if you're less than 7 things that you're going to hook up to on each of these outputs, everybody would just buy the 74LS in order for it to not get so hot. You don't want to waste all your power. And it'll run a little, it even runs faster than the 7400. And the only thing you got, to concern yourself with is that the 74LS is not going to be able to, it doesn't have enough energy coming out of it to drive as many gates as something like the 7400. Okay. Now, why these other ones? Well, obviously the S, if you need speed, it's the one you want. H, well, I've never used an H. Okay. These were probably faster and invented before the S, because a lot of times you got to look at what years each one of these things were released. The 7400s were first, and then I think they had the low power one came out second. But look at how much slower that thing runs. If you got the time, then great. Yeah, that's what you want, right? These Schottky ones, these are based on Schottky diodes. That's what the S stands for, I think. So this was running really fast. Like I said, it takes even more power and so on, right? So you can jockey these parameters around, and that's the whole ball game. People ask me, can I substitute this for that or whatever? Well, the answer is look at these numbers and ask yourself, is it going to be okay? In your specific design, it may or may not be, depending on a few factors. Now, back in 1980, this was pretty much the only factors we were really worried about, in addition to the fan out. And I wish they would have shown that in here. But the reason they don't show it in here, by the way, is it's well known that the fan out of a 7400 chip is some number X. The fan out of an LS is some other number. It's not going to be in a book like this. They wouldn't put it in every table on every page. It could be the same thing over and over and over and over again. There's usually a summary discussion somewhere in a book like this that says, the 7400 series fan out is X, and this one is Y, and that one's Z. And then you don't have to have it all over every page. So the way this is presented, I would have expected it to be at the beginning of a chapter. I don't know. Anyway, so you move on to all these other ones. Who knows, maybe there's a little summary in here. Hold time. There's a bunch of definitions of various, blah, 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 V in, V out. What do all those little abbreviations mean? Currents, switching parameters, short circuit currents, and things like that. Well, the definition of setup and hold time and stuff like that, which is also something you got to take into account. It's very serious. If you follow my Z80 Retro, we talked a lot about this early on. We were trying to pick which gates we were going to use and how fast they all had to run and things like that. And, whatever. You can Google this. These are well-known terms. You can find that on the internet. If you don't know, if you haven't watched the other recordings, I wonder where the fan-outs are. They got to be in here. If there's a master guide, for crying out loud, they got to have a description of the... Maybe it's so well known in 1980 that they don't even have a section. Wow. Well, I don't have time to read this whole thing on camera, which I'm sure all of you are, crying yourself to sleep over. But you will see those numbers in the data sheets for the specific chips when you buy the actual ones from the manufacturers. So let's look a little bit closer at that sort of documentation. So if we do a Google search on logic families, you'll find the usual Wikipedia page and some guides from Texas Instruments and things like Fairchild Electronics and stuff like that. Let's look at the Wikipedia page first here, okay? So what do we got? The usual introduction. If you read closely in here, blah, 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 high speed, widespread use of transistors. We had vacuum tubes and so on. In here, I was in here earlier. What does it say? Yada, yada, yada. These were used for a short period in the 60s. On these machines here, the 4004 is the first, CPU in a single chip. 8008, which predated the 8080, which were PMOS. That was a different kind of technology. Generally, we don't use it anymore today. What does it say? Okay, here's the part. Today, only ECL, TTL, NMOS, CMOS, and BiCMOS are still in widespread use. ECL is used for high-speed stuff, but you're not going to see that as a hobbyist. It costs a lot of money, uses tons of power, gets super hot. It's like, picosecond type speeds. NMOS still mainly use VLSI, like CPUs and so on. Yes, that's what the Z80 uses, I believe. The memory chips that fall outside this article, yeah, that's fine. Present day, logic ICs are based on ECL, TTL, BiCMOS, and CMOS right there, okay? So these are the ones you're going to mostly see if you're going to, I'm going to go over to DigiKey or Mouser or something and buy some chips. If you want to know history, you can go through here and you can look about, what happened with this one, what's that one, what's an LS, what's an AS, an ALS, an F, all these different types of chips, okay? A lot more came along since the Master IC Cookbook that was published back in 1980. So what do we got here? RTL, DTL, this is from the 60s. So if you sort this based on their year of introduction, 1962, 63, 64, it's not until we get down into TTL here that we're going to, these are the familiar chips. TTL original series. What do we got here? The propagation delay, there's your 10 nanos, there's your 33 for the L, the 6 for the H, and the 3 for the S right here, okay? How fast can this thing go? Right, 25 megahertz for a TTL chip. Well, if you're going to get LS, where's LS? Down here. What column am I looking at? Yeah, so we can get up to 40. You can even go faster, right? So we start seeing some more of these characteristics in here. Again, to answer the question, what can I substitute? If you tell me to use an HCT, can I use an LS in there? Well, let's have a look-see. HCT should be in here somewhere. ACT, HCT, right here. So what do we got here? 9 nanoseconds for HCT. 50 megahertz. What's 0.5? Yeah, that's your wattage, your power. That's very low power. So that's low power. It's moving along nice and high speed. You got to look over here as well. This will only run at 5 volts. Some stuff will run at 3.3 volts, or both 3.3 or 5. So again, more parameters that we got to look in here. And look at these years over here. Okay. How come the HC and HCT family aren't in my Master IC data book? It's because they weren't invented until 2 years later after the copyright. And I'm sure this book is from 78, 79 or somewhere in here. So, which is, you get your F and your LS and your S and so on in there. Okay. So when it comes to substituting parts or understanding why one's chosen versus another, you got to look at what was invented at the time that the circuit was designed, or what era you're trying to thematically base your design on. So that's going to have a big impact, obviously. What's actually available to buy, and what was available to buy in 1976 could actually disappear by 2023, right? So, I mean, I don't even know if I can buy an F anymore or anything like that. You generally can get the LS and your HC and your HCT, very commonly available still today. And you can run all those at 5 volts. And then you start getting into this 3.3 volt stuff. See the AC, ACT, this one will run at 3, 3, or 5, that sort of thing. So you now have to ask, is it okay for me to put, a chip in there? If it's running at 5 volts, I can't run out and buy a chip that will only work at 3.3, like this right here. I can't use an RTL chip. Not that you would, but I mean, at 500 nanos of delay, there's a slow chip for you. But that's an issue, right? This particular table does not show. There you go, down here, the G. I've never heard of these. That happened just the other day. I guess the gigahertz speed chips. These are pretty fast. Wow, 1.5 nanos. 1125 gigahertz. How can that run at 125 gigahertz when the propagation delay exceeds 1 nano, which means it has to be less? That means that the signal can be going on and off on the input to the chip before you can even see the output. Which maybe this is the average speed, and this is the average propagation delay, and this maybe is the peak speed across. Maybe some chips in this series can go faster than others, and that's always the case when there's more than one function available in the same family. So maybe there's a little bit of that in play there. I would assume that this would always be the inverse of that, but obviously that's not true here either. So I'm not sure how that's the toggle speed. Well, propagation delay, yeah, okay, fine. I mean, we can talk more about this too. How long does it take the output of the gate to reflect the function that it's supposed to do when the inputs change? That's your propagation delay. And this is how often can it be, changed from 1 to a 0 and 1 to a 0 if the thing is doing some other operation. Those are not necessarily the same thing, although in most cases, like a regular gate, like an inverter or something, yes, they are very tightly related because the output won't change unless the input changes. So, I'm mildly questioning some of these relationships in here. What was this one? The power per gate. Yeah, so the power goes down as, people come up with better technologies and stuff like that. So we can save power. We can go faster, all right? So that's why there's so many different families, okay? And they get a little more narrative down here about a lot of things as well. Now, this document is very high level, very generalized, okay? Let's go back to Google and do another logic families or maybe a comparison or something like that. And here's these guides, right? So you got your TI logic guide. Now, I've seen a couple of these over the years. First thing you want to do is look at the year, 2017. This is recent enough that it'll probably reflect something that you could actually buy, right? What's actively being manufactured, and you'll see some of the usual suspects over here. There's your F and your TTL. There's your 7400, 74F, LVT. We'll talk about this a little bit more. And the HC and the HCT and the LVC, LVT, and all this other stuff, okay? So you got a lot of different things to choose from. There's your 4000 series. And then we get a new kind of a presentation over here. And these charts here start to show what's really kind of going on. Well, you not have to read all these tables and stuff like that. See these lines here that end at 3.5 volts? Guess what? These chips are designed to run at 3.5 volts or 2.5 or 2.7 or 1.8 or somewhere in this range, obviously. Greater than this and less than that. These are what we would quite often refer to as the 3.3 volt chips as hobbyists, okay? These up here are the chips that run up to 5 volts. Some of them won't run very well down here at all. And they really, really, really want to run only around 5 volts. Those are your TTL chips, your 7400s. And which are not even made anymore. If you can even find a supplier, which you probably can because it was so popular, so ubiquitous in the 70s, but not in heavy demand today. That being these guys right here, okay? Okay, so you see these colors like this red one, the HC, that's your HC family. Now, what do you got down here? This green one, what's the green one? There's your LVC, okay? And your AVC and your AUC, whatever that means, right? Which you can find out all about in here as you read through this document. But these chart here really is in your face. Some of these chips are for 5 volts, some for 3.3, okay? And you can match these colors up and see what's going on there. You can see some other charts down here, which will get into some other, parametric comparisons and stuff like that. So what do we got here? Okay, like I was saying, your 1.2, your 1.8, your 1.5, your 3.3, your 2.5. So that, depending on how you want to pursue, if you're making a 3.3 volt circuit, pick these chips, one of these. Okay, if you're making a 1.2, you got less to go on. Only some chips run that low. Apparently, there's a 0.8, right? As a hobbyist, I got the 3.3 and the 5. All right, these are the two that I tend to focus on. Now, they give you kind of a nice overview and a chart over here that says, if I want to, let's see, comparison of switching standards, okay? So this is, okay, as a hobbyist, this is like 90% of what you want to know is in this table right here. So let's zoom in a little bit. What is the point of this page? If I want to have a gate of type D, like TTL or CMOS or whatever, and the output of that I want to hook up to the input of another gate whose type is R, which is in this, the columns over here. What is compatible with what? Okay, 99% of G. Can I substitute a part? This is the table right here. If you have a TTL chip, it's a 5 volt chip. Can I connect the output of that to another chip that is also a 5 volt TTL? Well, yeah, all of them are going to be designed to go together. So your 5 CMOS can go to 5 CMOS. Your 3, yes, they're designed to drive chips in the same family. So this diagonal will be yes all the way along here. But look what else we got over here. Can I drive a 5 volt CMOS chip with a 5 volt TTL chip? And the answer is no. And the reason is in this chart down here. We'll look at that in a minute. So when you're asking the question, can I do this? Well, there you go. There's your table. Don't ask me. Ask the guy that manufactured it, designed it, and knows exactly what they're used for. Okay? Can I take a 5 volt TTL and drive a 3 volt TTL? And he says, yes, but you got an asterisk over there. See where it says requires a VIH tolerance. And what we call a 5 volt tolerant chip. I can buy a 3 volt chip. And in the spec sheet for it, it'll say, yes, it's designed to be driven by a 3 volt chip right here. However, if some of the chips in the low volt TTL family will have a special circuit on the input of the gate to allow you to put 5 volts into it, even though it's a 3.3 volt chip. So that's what the tolerance thingy down here means. And the asterisk means not all of them will do that. You have to read this data sheet, okay? Same with the 2.5 and the 1.8. Some of them are 5 volt tolerant, some of them are not. That's all that means. Okay, what if I got a 5 volt CMOS chip? Can I go to a TTL? Yes. Can I go to CMOS? Yes. Can I go this? Yes, 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 with 5 volt tolerance. Okay, so this actually is pretty nice. Why don't you use CMOS? Well, it has to do with what can you drive this from its input? Look at the CMOS over here. No, yes, no, no, no. The only way that you can drive a CMOS chip as an R over here is if you have a CMOS chip driving it. So if you have a TTL chip over here, you cannot take the TTL and drive it into the CMOS. That don't work so good, okay? Now we get into these other ones, the LVTTL and the 2.5 CMOS and the, your HCTs and all this other stuff, which kind of expands this table, as we'll see in a minute. So you can have CMOS chips that are being driven by TTL, and this can change, but in certain logic families. But as a general rule, the answer is no, okay? Now let's look at why this is true. I'm going to have to take a step back here a little bit. 1.8, 2.5, 3.3, 5-volt CMOS, 5-volt TTL. Let's just concern ourselves with the left three. You can figure the right ones out on your own if you care or want to work at the lower voltages. So these are your 0 volts to 5 volts. This is the TTL. What this represents is the sensitivity of the inputs, as well as what happens at the output of a TTL chip. So on the left is going to be, left and right, same thing. See, these are the names of the signals, and these are the volts that are these levels, right? So the output high, VOH stands for volts, output high. That's your minimum amount of voltage that will come out of a TTL gate when it's in a circuit and connected properly within the constraints of the datasheet specifications. It will guarantee that the output of a TTL, 5-volt TTL chip will be at least 2.4 volts if it is being driven to a binary 1, or high. Okay? Anything at 2.4 volts or over is fair game. And many, many TTL chips drive way down here, and that's the problem with CMOS over here, okay? Come back to that in a second. TTL output will be at least 2.4 volts coming out, when used correctly, when it's high, and it will be at most 0.4 volts when it's supposed to be at 0. That's what the OL and the OH refer to, okay? Look at this spec here, the input high and the input low, right? So there's this, kind of a gray area. Literally, it's gray in this diagram. This is what we call the noise immunity region. The difference between input high and output high is the output is guaranteed to be at least 2.4 or more when it's supposed to be a 1, a high. However, the input will assume anything over 2 volts is supposed to be high on its input. So drive it high with a little extra margin to make sure that if something else is a little out of whack downstream, or you're drawing too much current and it starts to droop a little bit, the voltage may not be able to drive as hard if you have a lot of, that's your fan out. If you hook up too many gates, or the signal trace is really long, or you got a load resistance and all this other stuff on there, this can start to droop down a little bit. Or you can even have noise induced on their circuit board from nearby traces and lightning striking down the road and stuff like that, which can cause this to glitch a little bit. So this 0.4 volts is your noise immunity, in case there's things a little wobbling or ringing and stuff like that. When the voltage is transitioning and stuff like that. Sometimes the voltage, if you have 0 volts coming out of a gate and you say, please change to 1, and it'll go up here and it'll go boing and wobble around a little bit before it settles down somewhere up here. And when it's wobbling around, it can bounce back down. And if it bounces too far, it might actually look like it went from 0 to a 1, back to a 0 and stuff like that. So this distance, the amount of noise immunity in here can be very important based on your design, depending on the environment you're working in. Look at what happens with CMOS. It has a lot, almost an entire volt here of noise immunity. That might be a good reason to use CMOS instead of TTL if your environment generates a lot of ringing noise and stuff like that, because this immunity, the region here is much bigger. And that's why we still have these other chips, all right? Okay. Now let's look at why we cannot connect up TTL to CMOS. Well, if TTL guarantees that the output high voltage could be as low as 2.4, it could also be as high as 5. But it could be as low as 2.4 and be legal and within the spec of the output of a TTL chip. That's a problem, because a CMOS chip says, look, my input high Anything less than 3.5, it's in the no man's land down here. I am not going to guarantee that I'm going to react correctly. So if you have a TTL circuit that doesn't drive its output at least up to here, and that's the absolute minimum, okay, then you can't drive CMOS, and you can't. This is a well-known thing with hobbyists and stuff like that. You can't do it, all right? So how do you get around it? Well, sometimes you can take maybe a 2.2K resistor, and on the output of the TTL gate, tie the output to VCC, and that'll pull up on this a little bit, and quite often it'll pull it up more than enough that is needed, and you can just hook it up to CMOS with an extra pull-up on there, which gets us to, gee, I wonder why people like to put pull-up resistors on a lot of their circuits and stuff like that. One of the reasons is because of this. Okay, but as a general rule, you don't drive CMOS with TTL, it won't work. Nor will it work with this or this or that. Nothing can drive a 5-volt CMOS if it doesn't get you at least 3.5 volts or more. Okay? And none of these are going to do that. That's why that column was all no up here when it says, oh, can I hook up this thing? No, nope, just that one. All right, so let's look at the 3.3 then. Look what happens in here. I can take a 3.3 volt TTL gate, and its output will be guaranteed to at least be 2.4 volts when it wants to be high, and at most be, 0.4 volts when it's supposed to be low. It's exactly compatible with 5-volt TTL. I can take a 3.3 volt chip and take the output of a 3.3 volt gate, connect it directly to the input of a 5-volt TTL gate, and it'll work perfectly because of where these gray bars are in these voltage levels. Okay? Same's true with 2.5. Not so true over here, but you could do a 2.5 or a 3.3, and, this is not quite right. It only goes up to 2.3, okay? I mean, you want to be Wild West John Wayne and risk it all. I mean, it's close enough. You could probably get away with it for a hobby project. I certainly wouldn't use it for a medical device. But the point is the 3.3 volt is exactly compatible with the regular TTL. Okay? So what can you do here? This is your HCT, your ABT, your TTL, ACT, LV, blah, 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 blah. A lot of different families use these voltages here, and a lot of different families use the 3.3 in here. All right? So 5-volt CMOS, a little bit annoying to work with, alongside of TTL. You'll notice HC is in here. Okay? If your CPU is CMOS, and your RAM is CMOS, and your SIO, your serial ports and stuff, if all those are CMOS chips and their inputs are CMOS, you might need to drive them up high like this. And when I did the Z80 Retro design the first time, I used a different RAM chip on the board, and that RAM was rated at CMOS voltages. It wouldn't run down here. And this is why I started using HCT chips in my design, or rather HC chips, I should say, in my design. And it was because I needed to get the output driven higher. Today, in the Z80 Retro project, there's nothing on there that mandates 5-volt CMOS logic levels, in spite of the fact that I still have all HC parts in it to this day, which may or may not be the best choice. You could definitely take the Z80 Retro and substitute, HCT, certainly. Would have been that probably wouldn't have been a very good choice, because as we'll see in a minute, the difference between HC and HCT is that an HC part has the input and output characteristics as shown here, but an HCT part has input characteristics of TTL and output characteristics of 5-volt CMOS. Okay, so this would have probably been a better choice given the state of the project today. And if you really wanted to, you could use standard TTL parts on the Z80 Retro anyway, because I happen to know all the chips on there in the final design the CPU and the memory and the flash and the CTC and the SIO and all that other stuff. All those CMOS parts are TTL compatible on their inputs. So you could use these other parts on the current design of something like the Z80 Retro. Okay? So this is getting you kind of into the feel of this whole thing, right? What does the range of voltages have to be? What is your input tolerance supposed to be? Do you need to be able to read an input from a chip that has output values in this range? Can you, can you be greedier? Do you require more like this? And what do your outputs need to be? If you got a 5-volt memory that has CMOS voltage ratings, you need to have a gate. You don't need a gate that has an input rating like this, but you need a gate whose output rating is like this. And this is where it starts getting interesting. So a lot of the modern families, like this thing here, has output ratings of CMOS, input ratings of TTL, which is going to be able to be used in a lot of different environments. So as you go down through here, it'll talk about what kind of packages can you buy these things in. Here's the gigantic dips that we all love as hobbyists because you can stick them in the breadboards, poke your wires in there. You can actually pick it up with your hand, and it's not a problem. You get these little tiny things like these guys, it starts getting a little more difficult to solder them in, and especially when you get the QFN. Look at that thing on this guy. I don't want to be dealing with that. So sometimes the parts you want are not available in these, relatively speaking, gigantic packages that are easy for beginners. If you want to hand solder something, these are real easy. All right, you can do this, okay? Not so much maybe with something like that. Hand soldering these guys start getting a little bit more difficult to do. I've actually done one or two of these myself just to see if I could do it, and I was shocked when it actually succeeded and worked. Look at this thing. If we zoom way in on here, you can start to see what's going on there. What happens with these little guys, they don't even have leads sticking out. They're just little metal, like corner contacts here. This one has a pad underneath it too. So you have to solder, to this pad in the middle, and you got to solder around these outside things. The ones that I've been able to do by hand don't have the middle pad. They just have these little corner things here. QFN, I think N stands for no leads, as in sticking out of the package. But you can do these because usually there's a little bit of metal kind of sticking out on the side. And if you got a pad on the PCB that sticks out a little bit, you can kind of heat up your iron with a blob of solder along the side, and then just kind of like slowly drag the soldering iron through there, and then look very closely to make sure you don't bridge it and stuff like that. And you can do these. If you have a pad on it and you want to do that by hand, what I would do is I would put a hole in the PCB that's plated, of course, and then you can actually just stick your iron in that hole and fill up the hole with solder and leave it in there for a little while and heat up the whole thing, and it'll adhere. It'll work. I've done that as well. Once I even stuck a wire in the hole. You first solder it down around this way, and then you flip it upside down and put a wire in the hole and heat up the wire and solder the wire into the hole so that you have a good thermal conductivity out into this pad in here. Even if it's not soldered on a hobby board, the wire will be crushing into the bottom of this thing, and will probably make good enough contact for certainly a prototype, which is what I was doing at the time, and I never had any problem with that style of working. However, I don't want to do that every day. Stick with these over here whenever possible. And then you get these these are really difficult for me to solder in. You can do this with hot air. These are like ball grids without the balls on them. These are just metal surfaces on the bottom, a land grid, sometimes it's called. Maybe that's a manufacturer's name or something like that. But anyway, you can put solder paste down in the same pattern, and you heat up everything, the board, the chip, everything. You can use a hot plate and something like that to solder something like that in. These are super duper tiny. And then we get another one of these charts with a little more detail in it. And we have like all the chips over here Then we have, here's all the voltages that they run on. And what can you buy? What functions are available with these kinds of gates? So look what happens here. Some of these things like LVC, a lot of check marks. Other ones like LV1T, not so many check marks, okay? So what does that mean? That means that LVC chips are available to provide a wide array of different types of functions and gates, encoders, decoders, shift registers. There's a lot of products that are designed using this technology, LVC. Not so many for the LVT, or the LV1T, I should say, okay? You can only get buffers and line drivers and in discrete gates and whatever level transitions. These are like for your 5-volt tolerant input type of things. What else we got in here? Partial power down and all that. These gates that supply that provide partial power down are kind of neat. They allow you to power down the chip even if the inputs are still being driven, and they're designed in a way that they cannot or they won't parasitically sink a lot of current when they're off, which normally a chip would do that. And you're never supposed to have the inputs being driven on a chip that's powered down, unless, of course, it's designed for that purpose. So you can get that with this family. That's what that means. What else we got here? Over voltage tolerant input. So yeah, maybe they're 5-volt tolerant, stuff like that. We saw that above. It doesn't have power off, output disable, whatever that is. Power up 3-state, bipolar. Yeah, you're not going to find bipolar. That means TTL. That has actual transistors in it. CMOS means it has FETs in it. BiCMOS means it has some BJTs and it has FETs in the same part. Okay, so you can start to see what's going on here parameter-wise. Some of these are really special purpose, ALB, right? You're only going to get transceivers that are designed using BiCMOS technology and inline drivers. You're not going to get an AND gate that's an ALB a family device. Okay, why? Because they don't make them. These are very specific parts. All right, so that's when you start learning what's going on in here. So you're going to see people using things like the LVC chips are fairly common on hobby projects because there's a wide variety of functionality available. This is a general purpose family. So is this one down here, the LVA, right? But we got 3.3 and 5 volts. That's why HC, you can get these in 3.3 and 5 volt type of applications. They don't have as many functions as the LVA, but that's okay. You know, as long as it gets what you need, as long as you get what you need out of it, I should say. All right, and it goes on and on to all these other ones, ACT, HCT, F, and so on. Here's the HCT, the LS, and good old TTL way down here, your 7400 series. 5 volt only, all right? So 5 volt only chips, 3.3 volt only chips. Some of these might be 5 volt tolerant, but you got to look up the data sheet to know for sure. These chips you can power on either 3.3 or 5 volts, the same chip. You know, you just plug it into the board. It doesn't matter whether you're running it at one voltage or another, right? And some of these go down all the way to 0.8 volts and stuff like that. All right. So this is what you got to familiarize yourself with. You know, if you really want to find out, you know, can I do this? Can I do that? I'm out of stock. I can't buy a 74 LS, you know, whatever, 00 part. Can I put an HC in there? Well, maybe, but that's going to have CMOS requirements on its inputs. But if you put an HCT in there, that would be compatible. And it might even run faster. So let's click on that and have a look-see. You got your AC, ACT, HC, HCT, blah, 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 blah. What does it say about it in here? So it says, look, here's some sample typical devices, a 373, your 245, okay? What does it say? Well, when you're running it at 5 volts, it can drive 24 milliamps, and whether the voltage is a high or a low, it'll drive 24 milliamps. Some of these families, it'll drive like 64 milliamps when it's a high voltage, but it will only drive or be able to sync, you know, say 30 milliamps when it's low. It's asymmetric. Okay. And TTL chips, for example, if they're even in here, still give you the specs on them. When the output is low, they can supply a huge amount of current, relatively speaking, to when they're high, which is why very often you'll see in a design where there's an LED hooked up to the output of a gate, that gate will be set. I'm looking for the TTL ones. Let's see if we can get the numbers here. Well, you would design the circuit so that the LED only goes on when the output is a 0. This is why 0.4 milliamps is all you can pass through the output of a gate when it's a high. Okay? This is why you don't light up an LED with a high voltage coming out of a gate. You only set it up so that the LED goes on when the output is low. Okay? That's why. And to this day, you see that even when it's not necessary. I find myself constantly looking at my circuits and thinking, oh, I really shouldn't light up that LED when there's a binary 1 coming out of this, gate when the high voltage is there, because in the 70s, you couldn't light an LED if you wanted to, right? When it is high, you had to do it when it's low. Here's some other gates up here that are asymmetric: 15 high, 64 low. Okay, and that's your FCT, right? So here's a 1 and a 20 on the fast ones. What's a BCT? I've never used that. I don't know. But again, asymmetric, okay? Very common to see asymmetric outputs. Some of them are perfectly symmetric, but not always, right? Here's your 3264, your ABT. All right. And so on. Here's your LVTs. Yeah, these are the ones. An LVT means that you have low volt with TTL compatible inputs. Okay, it's a CMOS chip. That's what it says, rail-to-rail switching. What that means is that it's compatible with that chart we saw earlier. Let me go back up and show it to you. When people talk about rails, they're talking about the power, the 5-volt rail and the ground rail. So in order to be CMOS, you need to drive it to the rails from 0 to 5, or it won't work, okay? You need this really wide thing in here. TTL can drive that far, and you can certainly use rail-to-rail drive as an input to a TTL, but TTL simply doesn't guarantee that it'll drive it up to the 5-volt rail. It'll drive it down to 0. In fact, it'll do it even better than CMOS will, but it will not go up to the 5-volt rail, okay? This is the key. No matter what you hear from anybody about logic families, or, oh, we're using this transistor and this doping and this epitaxial, blah, 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 blah. Look, it's these diagrams right here, okay? That's all you need to know, especially as a hobbyist. Can I hook these together? It's all in that chart right there. What do I want to buy if I want to run it this, that, or the other voltage? Well, you need chips of these classes here, right? And the common ones are going to be your HC, your HCT, your LVT, your LVC, and your LS. I mean, you're not going to go too far wrong if you use those particular chip families, all right? All these others exist because they have different drive capacities. They have different speeds. They might behave differently in a battery-controlled circuit where the voltage is going down. What happens when the voltage browns out when you use this family versus some other family, okay? That's when you start getting super sensitive to, oh, I need an AUP1T with an input hold and a blah, 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 blah. All right? Those are all application, super-duper detail type things. General hobbyist stuff, though, you can stick to the common and popular ones. And the reason they're popular is because you got a wide variety of choices on your LVCs, okay? And your, whatever, your TTLs and your LSs. You got a lot more LS things out there than you do the S, for example, right? So stick to these common ones. They'll be widely available. They'll be manufactured by more than one source. The prices will be relatively low. It's everything you want as a hobbyist, certainly as a product designer as well. And if and only if you need something to behave in a very specific sort of way or operate at a unique voltage for your specific app, then you start looking at all these other families. Okay? Now let's do a search on the word hold. No, that's not what we're looking for. See, we got bus hold right here. This is kind of a neat feature. All right. Let me turn off the search highlighting here. Look at this column. So ALVC has products that support this so-called bus hold, as does AVC, as does LVC, and several of these other ones down here as well. The ALVT. Oh, I lost my column. Is that, yeah, this one here. And there's a little footnote here, so maybe some of them do. In fact, there is. That's by what it says. It'll be not all, but some of the LVTs will do it. The VME, the ABT, what do we got down there? The ACT, the FCT, and so on. Also available in automotive grade. Okay, great. Automotive grade, again, another classification beyond these. Usually automotive is going to be... what is that? Temperature extremes and stuff like that. It'll have, different tolerance to heat or, power dissipation and stuff like that. So anyway, let's look at bus hold. All right. Let's search for it again. Bus hold. Because this is kind of cool. Bus hold option. And there. Okay. Oh, it doesn't define it. Well, let's look at some chips that actually have bus hold and see what their actual data sheets say about them, okay? This one does. I know it because it's LVCH, all right? Texas Instruments, that's their naming style. If it starts with an SN, it's made by Texas Instruments. All their chips start with SN. The X means it could be a 74 or a 54. The 54 is like military grade or something like that, and 74 is industrial grade. Well, again, it says here's all the different kinds of part numbers for all the different kind of packages and their sizes and all that other fun stuff. Then it should say the 54 or the 74. 54 octal is designed for 2.7 to 3.6 volts. And this 74 is designed for 165 to 3.6. So this one has a more strict, voltage range. For the 54. I think the 54 is military. Is that right? I don't know. Somebody post in the notes below. I'm embarrassed not to know that. It's easily Googleable. Just look it up. Anyhow, all these little chip wires you got to get caught up in. But as a hobbyist, you pretty much don't see the 54s. You see the 74s. So this is a low volt CMOS is what that stands for, which means it's a 3.3 volt thing or less, right? In this range for this particular chip. The H means it has bus hold, and we'll see that in a second. It'll say mixed signal and some other stuff. Here's your live insertion, partial power down. We'll look at that in a minute. This will be a good data sheet to read because it'll define what all these things are. Bus hold on data inputs eliminates the need for external pull-up or pull-down resistors. And this is kind of a cool feature, okay? That's what we're looking at. It's the main reason I want to look at this data sheet, okay? We'll try and scoop up some of the rest of this stuff as well if you're not familiar with it. Okay, so this specifically states that it is 5 volt tolerant, okay? And therefore you can use these in a mixed 3.35 volt environment. Like I said, a bunch of different chips, packages, styles, and things like that. And it gives you a simplified schematic. These gates here with this resistor, these are your bus holds. Okay? Let's find the little narrative on there and talk about it. But look at what this is. I have a gate, a non-inverting buffer. And another one coming back at itself. So if there's a 1 here, this buffer says there shall be a 1 over here. And if there's a 1 over here, this gate says there shall be a 1 right here. With a little resistor over here, which will keep it set to 1. So if this pin here is not connected to anything, this gate would be floating and it might bounce around a little bit. But this gate here, no matter what it's doing, is going to be outputting something. And if this input here is floating, in other words, not connected to anything, then whatever this gate is doing, it doesn't matter what, through this resistor, and we'll talk about the resistor in a second, will drive this gate to match whatever's coming out of here. And once that happens, this gate here will drive it to do what it has been doing, and it'll latch up and stay that way. This is bus hold. Simple as that. This gate here basically feeds back and drives itself so that it basically cannot change unless something happens on this input that drives this resistor's ability here to try to keep this thing from ever changing. Okay? And that's all it is. Nothing more to it. And this is, I think the equivalence of this thing is a couple of K ohms or something like that. It may get into more of the details later on, or there might be another document that says, talks about bus hold in general across the TI lines and how to use it. But I think there's usually a little blurb on it in here. They might even have a rating in here somewhere that says, the bus hold resistor will look like such and so ohms. That's what I'm looking for, horseshoes over here, to see if there's a ohm rating for that. Nope. No horseshoes on that page. Or this one, well, here it actually gives you a current rating where it says input hold current, microamps. That's not a lot, okay? So they could either tell you, the resistor in the circuit is, this size. You can calculate how that will impact your other circuitry. Or they can just say, look, you're going to have to overpower that hold circuit by supplying at least 75 microamps, which is like nothing. Okay? What are we doing here for the input 0 to 3.6 volts? I'm not sure what this means. Is that during a transition? What's the 2 mean? The bus hold maximum dynamic current requirement to switch the input from one state to the other. Yeah, that's what it means on number 2. So what happens is this thing will consume about 75 microamps when it's stable. But when you're trying to change it from, 0 to 3.6 or whatever, it's going to require 500 microamps to overcome that, to overpower that resistor to switch that input. Now, this is actually pretty decent. And one of the huge benefits in here is you design a circuit and you just say, I'm going to pull up resistors on my bus. And one of the reasons you do that is because if nothing's driving your data bus, for example, in your design, you don't want it floating. That's a very bad thing to happen because CMOS gates, if you have any CMOS circuitry in your design, when it's floating, has a tendency to oscillate at a very high frequency, generating a morass of noise in all kinds of circuitry and stuff like that, and consuming an insanely huge amount of power and radiating a ton of RF energy into the air, interfering with radios, TVs, and phones all over the place. You don't want it to do that. It can also cause all kinds of parts of your circuit to fail and things like that. Because, if somebody just starts squawking, a couple of tens of megahertz of just random noise out here, not a good thing. Okay. My point is that 500 microamps is what it takes to overpower this resistor in here, to force this gate to output the signal that's coming in over here. If it's currently a 1 and it's held at 1 and I want to go to 0, I got to overpower this thing. That's all that means, okay? So that's what it means for the 500, right? But then there was that other rating, which was like, what was it, 75 microamps or something like that? Well, the 75 is, what if the value here is the same as, which is what soon happens, if he goes from 0 to 1, for a brief period, he has to overpower this thing with a 500 microamps to get this thing to flip its signal, come back around here, and now this gate is driving the same, high or low or whatever, the same state that A was over here when it was overcoming that. Once this thing settles down after flipping, this gate agrees with A, and A is not overpowering anything. They're both trying to make this gate here do the same thing anyway. So you have this notion of a dynamic current during the transition of a state from 0 to 1 or 1 to 0. And then you've got the static current that it takes to simply maintain the state that it's in now without ever changing again. All right? So that's what they mean, the dynamic and the static part. And this bus hold is kind of cool. It means you don't have to put a bunch of resistors to pull up your data bus. It's being done right inside here. Thank you. Saves you board space. Saves you cost. Okay? Now, these chips tend to cost more money if they have bus hold, but that's okay. If the increase in the chip price is less than the increased cost of these square inches on your circuit board to hold all the resistors, plus the cost of resistors, plus the cost of the assembly of putting the resistors in and the time it takes to do it and all the other stuff, this can actually be very cost effective, even if the chip costs you like a dime more to get the hold. It can save you money in the long run in the total cost of ownership and assembly of that product. Okay? So I wanted to make sure that we all kind of generally understood these different features when we talk about circuits, when we're designing circuits, and we're trying to pick and select a chip, that there's a lot of different things to choose from, and there's a lot of different kind of features like this bus hold, and whether or not I can put 5 volts into the input of a 3.3 volt chip. If I have a CMOS gate, what do I need to do? Can I hook it up to a TT? Well, no, not unless the thing is going to be configured to drive the, voltage all the way out to the rails as it shows up in here, okay? So that's what I wanted to make sure that everybody understood when it comes to logic families. So I'm sure I missed a million zillion things. Let me know your favorite little data points that have to do with choosing these different logic families. Honestly, I'd like to know. I don't do a lot of mixed stuff. I try not to, but these days it's hard. You got to do the 3-3 and mix it with the 5, and sometimes there's some CMOS in there, sometimes there's not. What are your favorite chips you like to use, and why? And where did you, what drove you to like a certain family versus another one? That kind of thing. Love to see it in the comments below. Thanks for watching. I'll see you next time.